I'm going to walk you through interpreting quadratics using technology. The first thing we want to do is graph our quadratic using our technology. Then we're going to use our graph to look at key features: the y-intercept, the vertex, and the x-intercept. Finally, we'll sketch a graph and interpret. Start by using technology to graph the quadratic. Replace variables with x's and y's. And adjust your screen so that you can see the y-intercept, the vertex, and the x-intercept. Now click on where your estimate of where the y-intercept is, and you can see that the y-intercept is exactly at 0, negative 9.444. Do the same for the vertex. And the x-intercepts. Now sketch a model of your graph on your paper. The graph is primarily in the first quadrant, so I've chosen to enlarge my first quadrant relative to the other quadrants. Plot your key points. Now connect the points, making a curve. So now we have a rough sketch of our quadratic. Let's label the axes to help us interpret. Our input is speed, so the x-axis we can label as speed, and the y-axis is G, or average fuel efficiency. Now let's start interpreting what these mean. The y-intercept tells us that at a speed of 0, we have an average fuel efficiency of negative 9.44 miles per gallon. So we don't even get miles per gallon. It's saying we're using fuel when we have no speed. So our y-intercept here doesn't make sense. That means that this model must have a limited range where it makes sense. Our y-intercept does not make sense, because ideally you would think that if the car isn't running, then you'd have a fuel efficiency of 0. You'd get 0 miles per gallon because you're not moving at all. So for this context, we have to think, okay, fuel efficiency does not make sense when the car is not moving for this particular model. This model might have uses in other places, but not for a not moving car. If we look at our first x-intercept, it says 6.7, 0. So this is saying when our speed is 6.7 miles per hour, we're getting 0 miles per gallon. Again, this does not make sense in context, so that one does not make sense. Maybe we're having very low fuel efficiency at 0. And then at our vertex, what this says is if our speed is 53 miles per hour, we get 30 miles per gallon. And that is reasonable. Our speed is 53 miles per hour, we get 30 miles per gallon. So this could be a reasonable model for fuel efficiency right around the vertex. And because the vertex is our maximum value, it also means that this is the highest fuel efficiency we're going to get, 30 miles per gallon. We're never going to have a more efficient car than if we're driving 53 miles per hour. So 53 miles per hour must be the optimal speed. Because once we get up to our other x-intercept, which is 100 mile per hour, it says our fuel efficiency drops back down to 0, which means that's very bad fuel efficiency. We're getting 0 miles for each gallon of gas. That means we're burning through gas very quickly at 100 miles per hour. So again, this does not make sense. So what we're seeing is that for this quadratic, it has really limited values that make sense for this scenario. The only one that really makes sense is the vertex value and the values closely around the vertex. And you'll find that not all models are good models. And looking at the key features of quadratics can help us determine when they might be good and when they might not make sense.